Okay, so for your graphic organizer for chapter 12, give it a title, make sure your name is on it, okay? We talked about the 4 sections. The very first thing we did in chapter 12 was looked at inverse variation and graphed rational functions. We moved to dividing polynomials using long division and simplifying rational expressions, which felt familiar. And then we multiplied and divided more complex rational expressions. Finally, doing the toughest operations, which were adding and subtracting rational expressions. And that's tough because what do you need when you add and subtract? Common denominators. That's what makes it tough. So let's start in section 1, inverse variation. What is the model, the basic little model of inverse variation? Good, y equals a over x. So one question might be, write an equation for x and y varying inversely when x equals 9 and y equals 2. You immediately write this little model down. Okay, and then we use what method for writing this equation? What do? We know x is 9 when y is 2, so we, substitution is what that's called, okay? So we have our model, y equals a over x. We substitute known values. 2 equals a over 9. And then we just isolate a, right? And the operation we'll use is, good, multiply by 9. And a equals 18. Now, this next step is where most people forget to take it this next step. You're asked to write an equation. So take this a that you found and substitute it into your model. Y equals 18 over x. It's an open sentence. I mean, we can now find any point that is true for this function. And the one value that may not be placed in the domain is 0 here, right? So that's it. Sometimes there's a follow-up question. What is the value of the function when x is 2? 9. And so you just go substitute back in and you find your value. There's another point. Okay? Then we went to the more sophisticated rational model, right? The more sophisticated model. Y equals a over what? X. Good. Minus h, I'm hearing it, plus k. That's right. That's the more sophisticated model because we can transform the parent y equals a over x. Y equals 1 over x. It's the most basic rational equation. We can transform it by doing a little something to our domain and adding something to the function. What happens when we alter h? What is that? H represents the left and right translation. Good. Okay. And so it's our vertical asymptote. H is actually that if we write this expression as x minus h. Then h is your vertical asymptote. It moves it left and right. And k is what? Good. Translation up or down, vertical. And the entire graph gives us a hyperbola, which hyperbola looks like what? Does it look like a U shape, a line, a S? 2 C-shaped branches. That's right, 2 C-shaped branches. Okay? There are things we can do to, there's something else we can do to transform this function. What if we alter the a? Haley, what if the a is negative, then what? It would be good, a reflection. So here's what I moved out. Find a little spot to put that. If a is negative, we have a reflection. And then if a is greater than 1, we stretch vertically. If a is a fraction between 0 and 1, then we have a shrink, as we've seen so many times. Okay, we're going to graph 1. And that's it. This is the deepest panel that you're going to. So this is the same panel 1, underneath panel 1, but we don't go this deep with any of the other topics. Down under, if you need to use another horizontal across the way. The method we learned to use in graphing was what? Remember? Just a table. Now, because you know a lot about these functions now, if I was to give you a multiple choice test, you might be able to find the correct answer without a table. Because you know, like, look at this equation. What x is not allowed in the domain? So we just said the domain, x may not equal -1, which means that x equals -1 is your asymptote, right? Is your vertical asymptote. So we could go plug that in. Whoops. It's a little out of alignment. Okay. And then what y value is not allowed? Y is not equal all real numbers except for 1. We can see that here, right? All real numbers except for 1. And so we could put that in. Whoops. It's out of alignment. So if it was a multiple choice test and you had 4 different graphs down there to choose from, you could go see which one has these asymptotes. If there's more than one with these asymptotes, then you might need to do something more. But if there is only one choice with these asymptotes, you have enough here. You said that x may not equal -1, so we would put that in the center of our table. And then what types of values do we put into the domain? Do you remember? There was something we added to these domains that was really important. Fractions, right? So what's a little bit bigger than -1? Negative and -1/2. And then a little bigger is 1 or 0, and then you could do whatever you want. You could go to 1. A little bit smaller than -1 is -1.5 or -3/2, whatever you want to call that. Then -2, -3. And that's probably enough information because you know what shape these are supposed to be. So let's plug it in. If we plug in -1/2, I'm coming right here. -1/2 plus 1 is, I'm looking up here. -1/2 plus 1 is +1/2. So what is 2 over 1/2? It's 4. 4 plus 1 is 5. So we're just substituting. Go ahead and find these values and come back. Okay, so we filled in the table. We have what we would expect. 2C shape, curves, the hyperbola, which do not cross those asymptotes. And please include the asymptotes in your graphs. Right? So as far as the transformation goes, how has this been transformed?
Up 1 to left 1.
Translation up 1 to the left 1, I'm hearing, and a vertical stretch. And the factor is 2. Up a factor 2. Okay? Good. Okay, let's back up to the second panel. Dividing polynomials, simplifying rational expressions. So take this down, come back. Okay, so we learned long division here, didn't we? So we have this y minus 3 going into this trinomial, y squared minus 5y minus 8. To make it tougher, we could have had these expressions not in standard form, right? We would have to put them in standard form then, and then we're ready to go. So we have this whole y minus 3, this whole binomial going into that. We look at the lead term, right? And how do we make y turn into a y squared? And multiply by y, so that's the first piece of our quotient. And when we do, we're now going to distribute that y to both of these terms, right? And y times y is y squared, and y times -3 is -3y. We need to subtract that entire expression. This is where some people forget to distribute your negative, right? So y squared minus y squared, but -5y minus -3y is what? -2y. And we bring down the -8. Now what will we multiply this binomial by to get -2y? -2. So when we distribute, we have -2y, what? What do we have? Plus 6. Okay. But we must subtract this entire term. -2y minus a -2y, we have opposites. We're adding 2y. And -8 minus 6 is what? -14. You've got to distribute that negative. Now we can't multiply y by anything to become -14, so that is your remainder, right? So we say there's two ways to say it. We could say plus negative 14 over y minus 3. Or you could say minus 14 over y minus 3. But there's your remainder, which is still being divided by the divisor. Okay, the next step was further division, but you felt like you were just canceling and maybe you weren't thinking of it as division. Canceling is division. Multiplication and division, multiplicative inverses, there's division going on there. So in this case, we did what? Factor, look for common factors and divide them out, right? A number over itself is 1. So we will factor these trinomials. Luckily, I mean, there is a coefficient in front of a, but it's a prime number here. So factor and come back and check it. So we have a factor over itself, a binomial factor, n minus 1 over a binomial factor, n minus 1. So we can call that 1, and there are other things going on, so we don't even have to write the 1. 3n plus 2, we can write this as 3n plus 2 over 2n minus 1. We don't even need parentheses. But what are the excluded values here? Good, you got to look up here. 1 is not allowed in this, and 1/2 down here. Plus 1 divided by 2. Okay, on to the third section, where we're multiplying and dividing rational expressions. Multiply. What's the denominator of the binomial 2 minus x? It's over 1, right? Okay, so really we can just take the entire, with multiplication, you simply multiply the numerators and you multiply the denominator. So we have negative 8x cubed, negative x cubed, and then we have this 2 minus x. I'm not going to bother distributing right now because we want to see if we have common factors in the numerator and denominator, right? So who has the factors of the denominator? Okay, so we have x plus 7x minus 2. Ooh, that's interesting. What do you see? We see opposites. And what does an opposite equal? Negative 1. So that's negative 1. So what do we have, Madeline? Over x plus 7. Good. And what are the excluded values? No, because negative 1 times negative canceled, or, gave us a positive. Excluded values, negative 7 and 2, because that was in the original expression. And then a division question. Simplify and come back and check your answer when you have tried it. Okay, multiply by the reciprocal, factor, keep factoring. There were 2 sum and difference patterns here. And then ultimately we could distribute this and call it 2w squared minus a w minus 6 or minus 7w plus 3. I mean, we could write it as the product of those binomials. Final section, adding and subtracting rational expressions. Toughest section because we need like denominators. So tell me the common denominator here, Cameron. What's the least common? What's the least common number 9 and 6 can both become?
18.
And then the smallest expression that a to the third and a could both become?
A to the third.
A to the third. So there's our denominator. So what did we multiply 6a by to get there? 3a. So we multiply the top by that. And we have 15a squared. This one we simply multiplied by 2. So we have 2. So our expression is 15a squared plus 2 over 18a cubed. Last question, solve this equation now. So we're solving for y. Now one strategy we learned was use a, multiply the whole thing by, good, the LCD. So that's what we'll try. Okay, so a lot of work to multiply by the least common denominator and simplify, and we ended up with two solutions we checked, and they will work. Good job, and do your